a very happy good evening. So this is Krishna Ma'am and we're talking about the story of life on earth, and that's biology. So thank you so much for joining me after the New Year's Eve, and I hope you guys had a very splendid New Year's Eve. You celebrated well. So I also hope you guys had a very good start. So hi W, yes, a very happy good evening. So thank you so much for joining my session this evening. Yes, I'm doing really good. How about you? So yeah, so I also wish you a very good start. So get into the track. So this year is going to be your career deciding year. So you're going to decide which college you're going to land up to. So which course you're going to take up to. So how are you going to give your needs? So a lot of things are going to be there here. So Keshav, hi. So is that you? Yes, I'm very good. How are you? After a very long time, where did you disappear? Yes, it's really happy. I'm really happy to see you here, Keshav. I hope you are doing good. Yes, Shubham sir, after a very long time you are here. A very happy good evening. So a very happy and a prosperous new year to all of you who are here with me for this session. Right, so and all of you who are watching, so please don't forget to like, share and subscribe, and please do lend us your support of spreading the channel so that it reaches a lot of people and I'm able to connect with a lot of students. Right, so we are in part 3 of biotech, ma'am. Biotech is pretty elaborate, pretty confusing because you're not able to imagine, and we still have a lot of to finish. Yes, I understand, but okay, so you're busy with your own schedule. All right, so I'm happy that you still remember me. So all the very best, Keshav, for the year. So I hope you become doctor very soon. So you come and tell me, ma'am, I have joined a good medical college and I'm going to become a doctor soon. So that is the message I'm expecting from you. So hope you do well, and anytime you have any doubts in biology, so please feel free to come and ask me, right? Fine. So we were here exactly talking about the cross verification step or the control point step, right? So this is lecture 3 of biotech. I'm done with the first 2 lectures of biotech. So where I taught you how we make a recombinant DNA, right? So now how do we confirm that it happens? So that is our next question now. So let's move forward. So let me, okay, so before we go, so I have to promote this. So please give me 2 minutes of your time. So they are starting an early class 10 and NTSE live course. So the course begins from 10th Jan. So if you have any of your siblings, any of your juniors, any of your cousins in class 9, so please let them know that there is a course, there is an opportunity like this by eCareerPoint, which says they finish their 10th standard portion much early, and they also train you for early NTSE. So guys, let me tell you, NTSE preparation by CareerPoint is well known, it's renowned, so you can easily guarantee them. So you have the benefits of the course, you have the features, so please do let people know and please pass on the word for me. So thank you in advance. Right, so we were here talking about the tools for recombinant DNA technology. So we first spoke about what are restriction enzymes. So today we'll be talking about cloning vectors, but before we actually go, so I will tell you what are cloning vectors, but before we actually dwell in deep about cloning vectors, we also have to talk about the cross verification step if your restriction enzyme has worked and if your plasmid has combined with the gene of interest. Right, so then we also have another tool that is competent host, but I'll give you a quick recap of what is that story that we were talking in the previous lecture, because we were talking on on Friday, right? And that's quite a long time. So here we go. So we were talking about the method of recombinant DNA technology. So this is in short written as rDNA technology. So how do we do? So you have A and you have B. So you take a particular, so this is the DNA of person A or plant A. So one particular gene is what you're interested in. So this is your gene of interest. So you have to insert this gene of interest into the DNA of B. So this is manipulating the genetic material of D, right? So now how do I do this? First, I have to chop my genetic material, the gene of interest, from the entire DNA. So the first tool that we'll be needing is the restriction enzyme. So restriction enzyme was found in E. coli when it was infected by a bacteriophage. So bacteriophage is the virus that infects a bacteria. So when the bacteriophage was infecting the E. coli, they found two types of enzymes acting to protect the E. coli. So the first enzyme was called as methylase, which adds methyl group to the self DNA. So whichever DNA has been made newly, so it quickly adds methyl groups, indicating that this is the self DNA of the organism. So there was another group of enzyme that is called as endonuclease, which chopped off the foreign DNA. So for all of you who do not know how the viral infection happens, the virus, so this is how your bacteriophage looks like. So the bacteriophage has the genetic material. So when the bacteriophage is infecting the bacteria, so bacteria has a cell wall, so it will only drop its genetic material. So its genetic material will go and integrate with the genetic material of the bacteria, and it will undergo replication, transcription and translation, because we have done the previous chapter. Now, if all of the self-bacterial DNA are having methyl group, so it is easy for the bacteria's immune system to chop off the foreign DNA, and it does it with the help of endonuclease. Thus, we are using this as our first tool in making the recombinant DNA technology. Yes, ma'am, a very happy good evening. So after a long time, you're here with me. So thank you so much. So please don't forget to like, share and subscribe. Right. Now, talking much about the endonuclease, so we call that as restriction endonuclease or restriction enzymes. So restriction enzyme belongs to a family of enzymes called as nuclease. So there are two types of nucleases. So we have endonuclease and we have exonuclease. So endonuclease chops off the double-stranded DNA at the particular position that you want. So it can cut DNA at specific sites, whereas your exonuclease chops off the DNA at the terminal portion. So this is the difference between both. So there are more than 200 restriction enzymes discovered. Actually, there are much more. So the first restriction endonuclease that was discovered was ECOR1. So E stands for the genus, CO stands for the species, that is coli, and R stands for the strain, that is being used, and 1 stands for the type or the number of enzymes that has been discovered. So ECOR1 was discovered, but much before that you had HIND2, which were discovered from Haemophilus influenzae, and this was the first enzyme to be discovered. So we use this to chop off the genetic material or the gene of interest that we need, right? So to make things pretty clear, so we have to take the gene of interest, put it in a vector first, and then insert the vector into B, right? So you take the gene of interest from here. So from the entire DNA of A, I have to chop this portion. So how will I know how to chop this portion? So to make it, yes, so the first restriction enzyme that was discovered was HIND2. Yes, I have mentioned here. So next comes ECOR1. So now, how does it recognize this space that you have to cut? Is because they cut using a recognition sequence. So each enzyme has a recognition sequence, and it makes sure it cuts in that recognition sequence. So this recognition sequence can sometimes be palindromic. For example, ECOR1, the recognition sequence is GATTC. Okay. So now your DNA is double-stranded. So let me write like this. GATTC. So now it is palindromic. So palindromic means whichever way I read, it is the same, right? Like Malayalam, like madam. So this is 5' to 3'. So this is 5' to 3' here. So if I give the restriction enzyme 𝐸𝑐O-R1, so 𝐸𝑐O-R1 will exactly cut at this point. So the pieces that I will have is GCTTA, right? And here I will be having AATTC, this is 3 prime, and here I will have G. So this is how I will have the cut segment. So these are called as the sticky ends. Fine? Yes, you're absolutely right. So now I cut this with a restriction enzyme, and plasmids are my vectors. So plasmids or my vectors are double-stranded circular DNA, right? So I have to cut the plasmid also with the same restriction enzyme so that I can insert my gene of interest into it. So I draw my plasmid like this. So my plasmid also has a sequence like this. So I use the same restriction enzyme to cut. So now these two are compatible. Say for example, this is my gene of interest, these and this two are compatible. So my gene of interest is loaded into the plasmid. So this is my recombinant plasmid now. So first step is done. But last class I ended on with a note, how will you confirm? How will you confirm that your restriction enzyme has cut at the right side, and how will you also confirm that your gene of interest has ligated with the plasmid or not? So that is the story for today, right? So for example, if I have a DNA and if I have the GATT sequence, right? So if this is the sequence I am looking forward to, and there are so many places in which this sequence is there. So there's a possibility that this can be repeated n number of times, right? So now if I give 𝐸𝑐O-R1, it will cut at every point that GATT is there. So it will cut at this point, it will cut at this point, so it will cut at so many points. So how will you decide which is your fragment or your gene of interest? So first of all, when you select your gene of interest, you should know the number of base pairs of your gene of interest. You should also know the restriction site that is present near your gene of interest. So these are the two prerequisites you look for before you start this process of restriction digestion, right? So now, for example, I have a DNA, okay? So I am giving 𝐸𝑐O-R1 enzyme. Say in this DNA, I have here GAATTC, so it is palindromic, so I write like this. So again here I have GAATTC, right? Now the length of this sequence, assume it is 500 base pairs. The length of this, assume it is 10 kilo bases. So kilo means 1000, right? So 10 into 10 power 3 bases is the size of this sequence and this sequence, right? So now I run an electric field. So I take a gel-like mat. This gel is made up of agarose. Agarose is a seaweed. So I take this agarose, so I have it commercially available. So I take the agarose powder from the market. So according to the prescribed measurements, I measure it, I heat it, and I solidify it. So it becomes semi-solid, okay? But at one side, I make depressions like this. So when it is very hot, when you pour it on a tray, so I make sure these depressions are made. So when they bake biscuit, so when the biscuit is hot, they make the seal, they make the impression, right? So similarly, when the gel is hot, I make this depression. Now the gel has solidified, it has become semi-solid, right? Okay. Now these depressions are called as wells. See, I cannot see any of this. It is microscopic. So, I will take the entire DNA in a small structure, in a small tube like this. The entire size of this tube itself will be 1 ml or 2 ml. Okay. So, such a small tube of 1 ml or 2 ml, we call it as a vial. Right. So, I take person A's DNA and then I had restriction enzyme. So, now what is there here? So, I have the DNA of person A plus I have my restriction enzyme. Right. So, now I have to see if it has worked or not. Right. So, that is my confirmatory step. So, I mix this well. Okay. So, now I take some amount and add it here, here, here and here. So, always replicates are very important when you do a life science experiment. Now, I connect this to an electric field. So, where DNA is noded, I have the negative side. So, the other side is the positive side. Okay, because DNA is negatively charged because of the phosphate group it has. So, I am connecting an electric field to this setup. So, from the negative side, it will move towards the positive side. So, ideally, when my echo R1 is given here, so now it should produce 2 fragments, one this and one this, because there are 2 sides like this. So, now the smaller of the fragment will run much quickly. The bigger of the fragment will stay here. Right? So, smaller the fragment, that will move away very quickly. So, smaller size fragments, they migrate faster. So, when I give the electric field, when I start the electric field is around 50 millivolt to 70 millivolt. Okay, so now when I add this mixture here and the mixtures here, so the electric field will show the migration of the fragments. But here, so there can be some intermediate pieces which is around 200 base pairs also, right? So there can be some intermediate pieces. So if I have a outlook like this, the final outlook like this, so how will I know which exactly is 500 or which exactly is 10 kilo base pair? So I should have the measurements written, right? So sometimes when you get a bucket, so sometimes on the corner of the bucket your markings are mentioned, right? So in your scale you have your markings mentioned, so you know which is 1 centimeter, which is 2 centimeter. So similarly, how do I know what is this size, what is this size, what is this size? Okay, so see, if you have to take a person's DNA, you can take from the person's hair, you can take from the, so probably we do not choose blood to take DNA because blood has more content of RBC and RBC is enucleated. So DNA is present inside the nucleus, right? So suppose if I want to take the DNA of plant A and put it inside plant B, there are ways how you can isolate DNA. So that I haven't discussed, that comes at the end of the chapter. I will tell you how to isolate DNA. Okay, so as of now, remember we have the DNA of patient A or the plant A and we are using restriction digestion. Okay, W, right? Yes. So now I should have some standard measurements so that I will know what exactly is my gene of interest. So I have something called as the ladder or the reference here. Okay, so this will tell me what is the base pair. Like this. So this will give me the standard size. So this is directly available in the market. So I take this and I load this also here before giving the electric field. So now this will also have patches like this. Now my gene of interest is 5 kilobase/pair. So I know the restriction enzyme has worked, and I also know which is my gene of interest among all the pieces, right? So our confirmation is done. But this is colorless. The gel is also colorless. Now, how will I track which has moved or which has not moved? So I add a tracking dye to this mixture. So when I'm loading, I add a tracking dye. So the tracking dye is bromophenol blue. But as such, it is not visible. So I can view these bands. So if I have to load this here, I should know it has been loaded or not, right? So there has to be some proof. Suppose if I am measuring from this height to this height, so I put a dot so that from here I can measure the next half, right? So now to know that I have loaded it here, to know my DNA is there, I added tracking dye, that is bromophenol blue. Now, these bands are not clearly visible only with bromophenol blue. So to the gel, while making the gel, I add a intercalating agent that is called as ethidium bromide. So ethidium bromide is ETBr. Okay. So when I add ethidium bromide at the end of the setup under the UV light, I will be able to see these bands as orange color. So this is how I cross verify if my restriction enzyme has worked or not. Ma'am, suppose other gene of interest also has the same base pair. How will you set in the same region? Then how do we know? Okay, so mostly no two base pairs or no two gene of interest has the same length, right? So probably it will at least differ in one base pair or two base pair. So here I gave you a very generalized notion. So this is 500 base pair, this is 10,000 base pairs, right? But what if this is 700 base pair and the other is 660 base pair? Accordingly, you will take a ladder. You will take a ladder which has very minute measurements. So here my measurements are pretty broad, but here I will take it accordingly. No two same region, no two regions with the same recognition site will be of the same base pair. That is very, very rare. So if in that case, you will choose a ladder which has very nearby measurements, not very generalized measurements. Okay, Kesha? Right. So this is how you confirm if your restriction enzyme has worked or not. Yeah, so guys, I want you to remember this. So this is a list of endonuclease which shows you which has what recognition site, exactly where it cuts. So if you look at the graph, arrow marks like this, it cuts here and it cuts here. So this produces sticky ends. But when it cuts exactly in the center, so the two pieces will be like this, right? So there are no sticky ends, so we call this as a blunt end. So remember, this is blunt end, this is sticky end. So please remember the example for each of these, right? So yeah, this is what I called as a vial. Right? So here is the DNA of the plant A or organism A. So I add my restriction enzyme in drops. Then I incubate it at 37 degrees for 1 hour. So I am giving or subjecting my DNA into or with my restriction enzyme. Right? Now, how will I know if my restriction enzyme has worked or not? So, I use a technique called as gel electrophoresis. So, in gel electrophoresis, it moves according to the size. So, separation happens according to the size. So, I will show you. So, at the end result, this is how it will look like. So, this is my ladder or my reference. So, this is higher weight molecule or heavy molecule, and this is my lower molecule. So this is how my fragments have moved. So now based on this, say for example, this is my 500 base pair. So yeah, this is it. This is my gene of interest, right? So probably if I run the same, say for example, this is from person A, this is from person B, from both the people I want only this size, so I can take them, right? So to show you how the setup is like this. So this is how I make the gel. So I told you, no, you take the agar powder, you mix it in a particular proportion, you heat it and you pour it on a plate. So this is the gel plate. Okay. So on the gel plate, I make depressions like this so that I can load my DNA. This is the entire setup. So once my gel is done, I connect it to the power supply. So it runs from the cathode to the anode, from the negative charge to the positive charge, right? So this is the direction of migration. From the negative charge to the positive charge, because your DNA is negatively charged because of the phosphate group. Finally, this is your DNA. So this is how it is. So when you give the electric field, this is how they migrate. Smaller ones migrate faster and larger ones stay there. No, I haven't spoken to her. I don't know, maybe, but she's still in touch with me, but she never told me so. Probably she's preparing once again. Okay, done? Yes. So now, so you add ethidium bromide that I have told you. So that gives you the visibility with the under UV light. So now finally what happens? So in my gel, if this is my gene of interest, now I have to take this and put it inside my vector. So please pay attention. I have my DNA from A. So I have my gene of interest. So I have cut it with the restriction enzyme and I have done the cross verification step of gel electrophoresis. The same thing I will do with my plasmid. So I have isolated a plasmid and I have cut the plasmid with my gene of interest. I will also cross verify if my plasmid is properly cut open, right? So now from the gel, so now this is my gel. So my gene of interest is here. So from the gel, I have to take it. So when you take the piece of DNA from the gel, so that step is called as elution. Extraction from the gel piece or separate bands of DNA when it is cut from the agarose gel. So that step is called as elution. So in elution, you use elution buffer to dissolve the gel and separate only the DNA fragment that is needed, right? So you take the gel slice, put it inside your vial. So you add binding buffer, DNA binding buffer, elution buffer. So this you have a kit. You have elution kit. At the end you get only purified DNA fragment. So same thing you do for plasmid, the same thing you do for DNA. So now you take the gene of interest and the plasmid and you add an enzyme called as ligase enzyme and patch up both. So now our gene of interest is ready, properly cut. Now our plasmid is also ready. Our plasmid is ready, our gene of interest is ready. So now we have to join both. So in a small vial, so I have my plasmid. So from top I give my DNA or gene of interest. I also add an enzyme called as ligase which helps in joining both. So ligase is an enzyme that helps in joining both the gene of interest and the plasmid. So finally, ultimately, I want it to be like this. So this is my recombinant plasmid, right? But what guarantee do I have that my gene of interest has ligated with my plasmid? So again, I have to do a cross verification step. So this is my positive or negative selection. So I can do this with the help of antibiotic, or I can do it with the help of insertional inactivation. So before we talk about this cross verification step, we should also talk about the features of a plasmid. So plasmids are our cloning vectors. So now the next thing that we are going to talk is about cloning vector. So we are done talking about restriction enzyme and what is the step to cross verify if your restriction enzyme has worked or not. Now the next step is to talk about the features of an ideal cloning vector, how an ideal cloning vector works, and how do I cross verify if the gene of interest has ligated with the plasmid. Okay, so once if we do these two, almost 2/3 of the chapter is done. So the last 1/3 is how do you isolate DNA and how do you isolate plasmid. So that is a very easy step. Alright, so today we stop here because I have taught you one important concept of elution and gel electrophoresis. So please go back, read your NCERT and get back. So day after tomorrow, Wednesday, I will teach you the most important concept of cloning vectors and what is positive and negative selection. Alright, yes. Yeah, so now we have the gene of interest and the vector. So now we have to check whether it has isolated or whether it has ligated or not. So before that, we should also talk about the ideal features of the cloning vector, right? Yes. So this is my last slide. So once again, a reminder for this. So please pass on the word. So let people know, right? So there's a new vaccine for teenager. Name of that, okay? So did you start getting vaccine? Find out, Keshav. So again, it's in the name of COVID vaccine only. So it is for teenagers, they say. So if there is a name, you guys find out and tell me. So why don't you Google this? So it's officially, the permission has been granted from Jan 3rd to provide vaccines to school students, right? Yes, you tell me what is the name. Okay, you asked out to me in Telegram. Okay, yes, I will get back to you. Yes, Keshav, sure. So guys, if you genuinely like the way I teach you, so please do like, share and subscribe. So please join me on my Wednesday's class at 4:15 for we're going to talk about cloning vectors and the method to cross verify if they have ligated with your gene of interest. So until then, this is me wishing you abundance of joy, happiness, positivity. So stay tuned. I will meet you on Wednesday. So bye and thank you.